general relativity, step by step. Last time I promised to talk about the Lorentz transformations, and I'm going to talk about the Lorentz transformations, but I'm not going to derive them in great detail. I'm just going to give an example of the kind of thinking that's required. We talked about speed of light. We talked about oh, here we go. So we've got two coordinate systems. We've got my coordinate system, and I'm just sitting here in interstellar space, and some guy in a spaceship is hurtling towards me at speed v, and he sets up his coordinate system as well, and we want to make sure that physics looks the same to both of us. What do I mean looks the same? It's not entirely trivial what I mean by looks the same, but the kind of, oops a daisy, the kind of thing let me just get a new space here. The kind of thing I mean is if I do some kind of experiment with x and y coordinates, just Cartesian space, and I've got a little pulley and a little thing and just a little experiment, then if my friend comes along and says, well, I don't want to use your coordinate system, I want to use my coordinate system, which is rotated with respect, he will still see the same physical phenomena occurring, but he may well describe them differently because he's got a tilted coordinate system. So what looks like x and y to me, when I say something's moving along the x-axis, it's not moving along his x-axis. I guess you call it x dash, and y dash, it's not moving along his x dash axis. So he might describe it differently to me, differently from me, but he nevertheless sees the same physics. So the kind of things that we do are we use Einstein's wonderful thought experiment with two mirrors here. This is me sitting along there minding my own business, and I'm just going to bounce a photon backwards and forwards between these two mirrors. Distance L between us. So how long does it take? Well, it takes L over c, because it's distance over time, which is just equal to L in relativistic units, because the speed of light equals 1. I'll keep the c in because it's easier at this stage. Now, my friend is in a spaceship. Here it is. He's sitting in his spaceship. It's not a very good spaceship, but there it is. And he's travelling that way. So he sees the light bouncing between these two mirrored surfaces. He sees the light, and I'm going to use red for light, if I can figure out how that works. Just a minute. Red. Here we go. So he sees the light bouncing backwards and forwards like that. Now he sees a different description of things. He still sees this distance L, the transverse direction doesn't change, but there's also this extra distance here, which is t dash times his velocity v. Now why is it t dash rather than just t? It's because not all observers agree about the rate of progression of time. There's no way it can do. There is no way that my friend in his spaceship can possibly measure time the same way as I do, because the speed of light is the same for both of us. And he sees this light has travelled further for him because it's travelling along that diagonal path. How far has it gone? Well, it's his squared distance is going to be L squared plus V squared T dash squared, just by Pythagoras. So that tells me Vt dash, that tells me that T dash will equal D over C, where D is his diagonal distance measured in his coordinate frame there. So that tells me that T dash squared equals 1 over C squared times D squared, which is over C squared, and then L squared plus V squared T squared. Oh no, that's T dash squared, isn't it? T dash squared. And so that tells me that T dash squared times 1 minus V squared over C squared equals L squared over C squared equals T. So there's quite a lot going on here. What am I trying to say? I'm trying to say that in the dashed coordinate system, as measured by my friend in his spaceship, T dash, which is the time that he thinks the photon takes to get from there to there, satisfies this equation here. T dash equals D over C, where D is this diagonal, the length of this diagonal path. So we can fool around with the algebra, and that equals T. That equals t because that's how long I think, oh, that's t squared, isn't it? That's how long I think it takes to get there, because as far as I'm concerned, t equals L over c. So t dash squared, 1 minus v squared over c squared, equals t squared. And so that tells me, that's in brackets, that t dash equals t over root 1 minus v squared over c squared. And it's customary to write, not gamma, I'm sorry, it's customary to write beta equals v over c. So what that tells me is that t dash equals t over root 1 minus beta squared, where beta equals the speed of light in units of the speed of light, I guess. And it's usual to write that t dash equals gamma t, where gamma equals 1 over root 1 minus beta squared. So that is the Lorentz time dilation term, because we both measure time slightly differently. Now, I do not want to go on and on and on about how different observers and twin paradoxes and all the rest of it, because I don't want to get sidetracked into hundreds of screencasts about special relativity. I'm going to assume that special relativity is is reasonably well understood, and I'm going to introduce concepts like this as and when I need them. So that's the basis of the Lorentz time dilation, and I'll talk about Lorentz contraction in the next screencast. Stop.